Hello everybody, myself Shama Sri Kumar, Assistant Professor, Department of ECE, Rajagiri School of Engineering and Technology. Today we'll be discussing the Module 2 of Applied Electromagnetic Theory, and it deals with the electromagnetic wave propagation in different media. The topics covered in this lecture are the wave equations and the expressions for electric and magnetic field in the case of a lossy dielectric medium. So before we move on to the wave equations, we'll see what is a time harmonic field. Any field that will vary sinusoidally or periodically with respect to time is called as a time harmonic field. So if the field contains a term e raised to j omega t, it is an example for a time harmonic field. Now when you consider e raised to j omega t, it is a combination of cos omega t and sin omega t. Now when you consider any complex number, we can represent it in the polar form or in the Cartesian form. So it will contain an amplitude and a phase. So this complex number is given by, let it be z, which is equal to x plus jy. Now this will have a corresponding polar form which is given by r angle theta. This r angle theta can be written as r e raised to j theta, where r is the amplitude and theta is the phase angle. Now according to that is this e raised to j theta can be expanded as cos theta plus j sin theta. When you compare this equation with x plus jy, we will get x equal to r cos theta and y equal to r sin theta. Now, if you want to determine the amplitude in terms of x and y, you will get it as r equal to root of x square plus y square. If you take x square plus y square, you will get it as r square. So r is root of x square plus y square, and theta is given by tan inverse y by x. That's when you take sin theta by cos theta, you'll get it as tan theta. So tan theta equal to y by x, so theta equal to tan inverse y by x. So now let us consider a vector A which is given by A naught cos omega t minus beta x ay cap. It is dependent on cos, so it will vary periodically with respect to time. Hence, it is an example for a time harmonic field. So this A naught is the amplitude. From omega, you will get the frequency, and this is the phase angle. And this vector is directed in the y direction. Now, when you consider this, this can also be expressed as real part of A naught e raised to minus j beta x ay cap e raised to j omega t. Because e raised to j omega t minus beta x, if we expand this cos omega t minus beta x plus j sin omega t minus beta x. So if you take the real part from it, you will get it as cos omega t minus beta x ay cap. If you consider this term, it is independent of time. And when you consider the time factor, it is e raised to j omega t. So we can represent the remaining terms, that is by dropping the time factor, the remaining terms is called as the Phasor form of the vector, and it is given by as x, y, z. The subscript s represents the Phasor form, and this term will not be dependent on time, and it will be dependent only on the three coordinates. So the term which is obtained by suppressing the time factor is called as the Phasor form of the vector. Thus, vector as can be written as a naught e raised to minus j beta x ay cap. So its factors other than e raised to j omega t. So it will be a naught, and the phase angle is minus beta x, and it is in the direction ay cap. Thus, the vector A can be represented as real part of as e raised to j omega t. When you consider the time varying fields, if you want to separate the time factor, the e raised to j omega t will be taken outside, and the remaining terms will be called as the Phasor form of that corresponding vector. So now we have seen that the vector A can be represented as real part of as e raised to j omega t. So this as represents the phasor form of the vector and it is independent of time. Now let us try taking the time derivative of this vector a. When you take the derivative with respect to time, the derivative of e raised to j omega t will be j omega e raised to j omega t. As is a parameter which is independent of time. Thus, you can tell that if you are taking the derivative with respect to time, it is equivalent of multiplying the phasor form by a factor of j omega. Similarly, when you take the time integral of vector A, it will be equivalent to dividing this as by j omega because the integral of e raised to j omega t is e raised to j omega t by j omega. So when you take the integral, you are dividing by j omega, and when you take the derivative, you are multiplying by j omega. Now we are going to apply the phasor concept to time varying electromagnetic fields. So when you consider electric field and magnetic field, it depends upon the coordinate as well as time. So the field components, that is the electric and magnetic field, is a function of the three coordinates as well as time. Now when you consider the phasor forms of the corresponding fields, it will have a subscript s and it will be a function only of the coordinates. It is a factor which is independent of time. So we are suppressing the time factor and extracting the phasor information of the corresponding fields. So we have already discussed the Maxwell's equations for time varying fields. There were four Maxwell's equations starting with the Gauss law to the modified Ampere's law. And the corresponding point forms were given by del dot d rho v, del dot b 0, del cross E is minus dou b by dou t, and del cross H is j plus dou d by dou t. Now we'll extend this form into the phasor form. That is, we'll modify these expressions into the phasor form. So this set of Maxwell's equation is called as the time harmonic Maxwell's equation by considering the time factor as e raised to j omega t. So what will happen is that all the field components will be modified with a subscript s. So it is del dot ds equal to rho vs. Corresponding integral form will also have a subscript s because this denotes that these field component is dependent only on the coordinates. Even if it is a time varying field, the time factor will be suppressed and the others will be made as ds or es or hs, etc. Similarly, del dot bs will also be equal to 0 and this represents the corresponding integral form. Now, when you come on to the next Maxwell's equation, it was del cross E equal to minus dou B by dou T. The modification is that we had a differentiation with respect to time. It is replaced by multiplication with j omega. So a j omega will get multiplied here as well as in the integral form there was dou B by dou T. It is replaced by minus j omega into Bs. Now, when you come on to the last Maxwell's equation, which was the modified Ampere's law, it was del cross H equal to J plus dou D by dou T. There was a term dou D by dou T. That derivative with respect to time is replaced by multiplication with j omega. So it is j omega into ds. Similarly, in the integral form, there will also be a multiplication with j omega. So these four represents the Maxwell's equation in phasor form. So all of them is having a subscript s. Hence, these field components will be dependent only on the coordinates. Now we'll move on to the concept of electromagnetic wave propagation. So what do you mean by propagation? We are carrying some energy from one point to another. So we are using electromagnetic waves for carrying information or energy from one point to another. So we have to consider different medium through which electromagnetic waves can be propagated, and we need to study the difference between the properties of the waves as it propagate over different media. And the different media which we consider here are free space. So when you consider free space, the value of permittivity is equal to epsilon naught and value of permeability is equal to mu naught. And when you consider the conductivity, it is not a conducting medium, hence sigma equal to 0. The next medium which we have to consider is lossless dielectric. Lossless dielectric means since it is a dielectric, permittivity and permeability will be epsilon naught, epsilon r and mu naught, mu r. And when you consider a lossless dielectric, when you compare sigma and omega epsilon, sigma will be very much less than omega epsilon since it is a dielectric medium. So sigma can be considered approximately to be 0. The next medium is lossy dielectric. Lossy dielectric, here epsilon will be epsilon naught, epsilon r and mu will be mu naught, mu r, but it will experience certain losses as the signal propagates through the medium. And the last case is the case of the conductors where sigma is very much greater than omega epsilon. So sigma will be approximately equal to infinity. That is, sigma tends to infinity since it is a good conductor. It will have high values of conductivity. The value of epsilon and mu remains the same. So first we'll discuss the wave propagation in lossy dielectrics. Then we'll extend that concepts into lossless dielectrics, free space and conductors. So we are considering a lossy dielectric. It is a medium in which the wave propagates and it will lose power as it propagates through a lossy dielectric due to the imperfect dielectric properties. That is, it is a lossy. That means it is having certain imperfect dielectric properties. And when you consider this lossy dielectric, it is a partially conductive medium because it's not a perfect dielectric, neither a perfect conductor. So the value of sigma is not equal to 0. And now we are considering a linear, isotropic, homogeneous, lossy dielectric media. So linear means the properties are uniform throughout. Isotropic means that when you consider isotropic homogeneous medium, we consider the permittivity will be a constant value throughout the media. And this medium is assumed to be charge free. That is, the value of volume charge density will be equal to 0. So, to start with a derivation for the wave propagation lossy dielectrics, we will suppress the time factor e raised to j omega t. On suppressing the time factor e raised to j omega t, the Maxwell's equation reduces to the form del dot es equal to 0 since del dot d is rho v and we are assuming a charge-free region. Del dot hs is equal to 0 from the expression del dot b equal to 0. The next equation is del cross E is minus dou B by dou T. And when you reduce to Phasor form, it will turn out to be del cross ES is equal to minus j omega mu Hs. The last equation is from the modified Ampere's law, which states that del cross H is equal to J plus dou D by dou T. And when we reduce to point form, we will get del cross Hs is equal to sigma plus j omega epsilon into Es. So we have got two equations connected with divergence and two with respect to curl. Now we will take the curl of equation 3. So on taking the curl of equation 3, we will get del cross Es is equal to minus j omega mu del cross Hs. On observing the LHS, it is the curl of a vector. It can be equated using the identity del into del dot A minus del square A. And when you observe the RHS, we are having del cross Hs. From equation 4, we will get the value of del cross Hs. On substituting these two, we will get the expression del cross Es to the form del into del dot Es minus del square Es, and that is equal to minus j omega mu into sigma plus j omega epsilon Es. And this del dot Es is already equal to 0 from equation 1. So from equation 1, we know that del dot Es is equal to 0. So the expression reduces to the form del square Es is equal to j omega mu into sigma plus j omega epsilon Es. And this equation can be written as del square Es minus gamma square Es is equal to 0. That is by taking the term on the right hand side to the LHS and equating to 0. So when you compare these two expressions, we will get the gamma square value to be j omega mu into sigma plus j omega epsilon. And from that, we will get the value of gamma as root of j omega mu into sigma plus j omega epsilon. And this gamma is called as the propagation constant in the medium. And this gamma is made up of a real part which is alpha, and it is called as the attenuation constant, and the imaginary part is beta, which is called as the phase constant. And the unit with respect to which gamma is measured is meter inverse. So this gives us the value of gamma. When you find out the real part, you will get alpha, and the imaginary part will give us beta. So now we have obtained an equation in terms of electric field. Similarly, for magnetic fields, we'll take the other expression, which is given by del cross Hs is equal to sigma plus j omega epsilon Es. If you take the curl of this equation, this will reduce to the form del square Hs minus gamma square Hs is equal to 0. Instead of electric field, it will correspond to magnetic field, and gamma will be the propagation constant, which is equal to root of j omega mu into sigma plus j omega epsilon. And those two equations is called as the wave equations called Helmholtz equations, which corresponds to for the electromagnetic wave propagation. So both of them are second order differential equations corresponding to electric field and magnetic field. One is del square Es minus gamma square Es is equal to 0. Second one is del square Hs minus gamma square Hs is equal to 0. So for the propagation constant, we have got a real part which is alpha and an imaginary part which is beta. Now we'll try to determine the value of alpha and beta from the expression of gamma square. So gamma square can be written as j omega mu into sigma plus j omega epsilon. So this is the value of gamma square. Now when you take the expression gamma, you also know gamma is alpha plus j beta. So if you square this, so gamma square is alpha plus j beta the whole square. On expanding this, you will get it as alpha square plus j beta the whole square plus 2 alpha beta j. So we will get gamma square is equal to alpha square minus beta square plus 2 alpha beta j. So this j square is turned out to be minus 1. Now, when you consider this expression, if you separate the real and imaginary part, the real part corresponds to minus omega square mu epsilon. That is the real part from this expression for gamma square. And when you consider the magnitude of gamma in terms of alpha plus j beta, it is magnitude of gamma square is equal to alpha square plus beta square. So when you take the magnitude of this gamma square, you will get it as omega mu into sigma square plus omega square epsilon square. This is the magnitude of gamma square. Now, when we consider the equation B and C, when you compare those two equations, you will get beta square minus alpha square equal to omega square mu epsilon. And also by comparing the imaginary part, you will get 2 alpha beta is equal to omega mu sigma. That is, if you compare these C and A, you will get the imaginary part. So 2 alpha beta will be equal to omega mu sigma. So when you consider equation 4 and 5, you will on adding those two equations, that is 4 and 5, you will get it as 2 beta square is equal to omega mu into omega epsilon plus root of sigma square plus omega square epsilon square. So when you find out beta, it is omega into root of mu epsilon by 2 into root of 1 plus sigma square by omega square epsilon square plus 1. And this gives us the value of phase constant beta, and it is measured in the unit radians per meter. Since it is phase constant, it's a phase shift per unit length. It is measured in radians per meter. From equation 5, we know that beta square minus alpha square is omega square mu epsilon. So we already found out the value of beta square. So we'll get alpha square as beta square minus omega square mu epsilon. So this is beta square minus omega square mu epsilon. So on substituting and simplifying the expression, we'll get alpha square as minus omega square mu epsilon by 2 plus omega square mu epsilon by 2 into root of 1 plus sigma square by omega square epsilon square. So the value of attenuation constant alpha is given by omega into root of mu epsilon by 2 into root of 1 plus sigma square by omega square epsilon square minus 1. And this is the expression for attenuation constant alpha, and it is measured in the unit Weber per meter. So now we need to find a solution of wave equation. That is, we are having a second order differential equation. We need to find the solution to it. So we are assuming that the wave has amplitude only in x direction and the wave is moving in z direction. So the phasor form of the vector can be determined as Exs of z Ax cap, where Ax cap denotes that it's at amplitude only in x direction, and this z denotes that the wave is moving in z direction. So we can write that any electric field vector can have x, y and z components. So it is Ex Ax cap plus Ey Ay cap plus Ez Az cap. Now, when you consider the phasor form, a subscript S will be present in additional. So, since here we are having only the x component, you can write it as del square minus gamma square Exs of z equal to 0. So, this is a second order differential equation. We need to solve this and find the value of Exs of z. So when you consider this differential equation on expanding it, it will have three terms. One is dou square Exs by dou x square plus dou square Exs by dou y square plus dou square Exs by dou z square, and that is equal to gamma square Exs from this term. So when you consider Exs, it is a function, that is a wave is moving in x direction and this is a function of z. So these two terms will be equal to 0 since Exs is a function of z. So we are left with the last term. So dou square Exs of z by dou z square minus gamma square Exs z will be always equal to 0 since the wave is moving in z direction. So this second order differential equation can be solved using the concept of complementary function. So the complementary function is given by d square minus gamma square is equal to 0. From this, we'll get the value of d as plus or minus gamma, since d square is equal to gamma square. So if it has got two roots which are having equal and opposite sign, we know that the general solution is given by c1 e raised to, that is, there's a constant e raised to alpha 1 x plus c2 e raised to alpha 2 x. Here the two solutions are, one is e raised to minus gamma and the other one is plus gamma. And the amplitude constants are given by E naught and E naught dash. So the general solution is given by E naught e raised to minus gamma z plus E naught dash e raised to plus gamma z. Since our function Exs is a function of z, here it will depend only on z. Now, when you consider the wave, this term corresponds to the wave which is moving in the positive direction. Since it is an exponentially decaying function, it will reduce to 0 as z tends to infinity. Now, when you consider the first second term, it is the wave moving in the negative direction because as z tends to minus infinity, this will reduce to a finite amplitude which is 0. So when you consider the wave, we are assuming that the wave is moving towards infinity. So the electric field must be a finite value at every point. That's whatever point we consider, it should be a finite value. So if we substitute infinity directly here, this term tends to infinity. So the field can't be infinity. So since it should be a finite value, the value E naught dash will be equal to 0 in the case of the wave propagating in positive z direction. Hence, the electric field vector can be written as Exs of z Ax cap, and that is having the value Exs is having the value E naught e raised to minus gamma z. Therefore, the electric field intensity vector can be generalized as the form Ez of t is real part of Phasor form e raised to j omega t. We have already determined the value of Es. On substituting that, it is real of E naught e raised to minus gamma z Ax cap e raised to j omega t. So when you consider this gamma z, it is alpha plus j beta. So this reduces to e raised to minus alpha z, e raised to minus j beta z. So if you combine the terms omega t and beta z, this reduces to e naught, e raised to minus alpha z, e raised to j omega t minus beta z x cap. And this is the complex term in it. And if you take the real part of this, this will reduce to cos. Hence, the electric field vector EZT is given by E naught e raised to minus alpha z cos of omega t minus beta z Ax cap. And as you can observe from this, the wave has amplitude only in x direction, and it is a function which is dependent on time and it is propagating in z direction. And this shows that it is exponentially decaying as it moves towards infinity. And this gives us the expression for electric field intensity for an electromagnetic wave. Now, to find the magnetic field intensity vector, we are making use of the Maxwell's equation 3, which is given by del cross Es is equal to minus j omega mu Hs. So when you consider del cross Es, we are taking the curl of electric field. So on expanding it into the determinant form, we are having Ax cap, Ay cap, Az cap. The first row will be the derivative since it is a del operator. So it is dou by dou x, dou by dou y, dou by dou z. And when you consider the electric field intensity vector, it has amplitude only in x direction. So it is Exs 0, 0 since it has no amplitude in y and z. And this is equal to minus j omega mu into Hs. Now when you expand this, you will get that the y term, that is when you consider the ax cap term, it is 0 minus 0. When you consider the y term, we are having dou exs by dou z. It is equal to minus j omega mu into hys into ay cap. Since it is a component along y direction, we will take the magnetic field intensity component along y direction. So we already know the value of Exs. It is E naught e raised to minus gamma z. On substituting Exs as E naught e raised to minus gamma z, we should take the derivative with respect to z. So this term reduces to, that is this j omega mu hys, it is minus gamma into E naught e raised to minus gamma z. So that is given by gamma E naught e raised to minus gamma z. So if you find hys, it is gamma by j omega mu E naught e raised to minus gamma z. What is gamma? It is root of j omega mu into sigma plus j omega epsilon. On cancelling one j omega mu, we will get hys as root of sigma plus j omega epsilon by j omega mu into e raised to minus gamma z. So this is one of the forms of the expression for magnetic field intensity. Here, the term root of j omega by mu by sigma plus j omega epsilon is called as eta, and it is called as the intrinsic impedance of the medium. this is denoted by eta. So the expression reduces to Hs is equal to E naught by eta e raised to minus gamma z ay cap. Now, when you consider the vector h, we should multiply it with e raised to j omega t and take the real part. So, on substituting that, it is E naught by eta e raised to minus gamma z e raised to j omega t ay cap. Again, substituting gamma as alpha plus j beta, you will get this expression. On separating that, this represents the complex term. On separating the real part, you will get it as E naught by eta e raised to minus alpha z cos of omega t minus beta z ay cap. So this corresponds to the expression for magnetic field intensity vector, that is HZT. So where eta represents the intrinsic impedance of the medium. Now, when you consider the impedance, it is eta, it is root of j omega mu by sigma plus j omega epsilon. It is having a real part and an angle. That is, it will have a magnitude and an angle since impedance is an imaginary quantity. So, it is having a magnitude angle eta. It can be represented as magnitude of eta e raised to j theta eta. Hence, the magnetic field vector can be replaced as E naught by magnitude of eta e raised to j theta eta e raised to minus gamma z ay cap. So, this gamma is replaced with alpha plus j beta. And after that, we'll write the vector h using this form, that is real of hs e raised to j omega t. So when you substitute the value of hs, you will get the expression of this term. So when you consider the complex parameter, it is e raised to j omega t minus e raised to j beta z minus e raised to j theta eta. So when you separate the real part, the E naught by magnitude of eta e raised to minus alpha z is constant. We'll take it outside. Ay cap is also outside. When you take the real part, you will get it as cos of omega t minus beta z minus theta eta. So when we compare it with the electric field intensity vector, the amplitude reduces by a factor of magnitude of eta and there is a phase shift of theta eta. That is the difference between the electric field vector and the magnetic field vector. Also, we can observe that when you consider the wave, it propagates in the z direction and it decreases or attenuates by a factor of e raised to minus alpha z. So, this is the observation from this expression for magnetic field intensity. So when you consider the magnetic field intensity vector, it is E naught by eta e raised to minus alpha z cos omega t minus beta z minus theta eta ay cap. So this alpha is called as the attenuation constant and it is measured in Weber per meter. It is the rate of decay of the wave as it propagates through the medium. Now, when you consider attenuation of 1 Weber means that it is a reduction to e raised to minus 1 of its original value. That means e raised to, when you consider it in the log scale, 1 Weber means it is 20 log e, so it is 8.686 decibels. That is, as the wave decays, once it reaches the e raised to minus 1 value, it is said to have 1 Weber of attenuation. Now, when you consider the electric field and magnetic field intensity vector, there is a phase shift of theta eta. So, this is due to the contribution of intrinsic impedance. So, at any time, electric field leads magnetic field intensity, or in other words, magnetic field intensity lags electric field intensity by an angle of theta eta. Now we are having an additional term called as loss tangent or lossy tangent. So from the modified Ampere's law, we are having del cross Hs is equal to sigma plus j omega epsilon Es. So when you consider this equation and if we take the ratio of conduction current density to displacement current density. So conduction current density means magnitude of sigma Es and displacement current density corresponds to magnitude of j omega epsilon Es. When you take the magnitude, you'll get it as sigma by omega epsilon. And that is represented by constant with the tan theta. And this is called as the loss tangent or lossy tangent. That is tan theta equal to sigma by omega epsilon. And that is called as the lossy tangent or loss tangent. Now, depending upon the value of sigma and epsilon, we can decide whether it is a good dielectric or a good conductor. If sigma is very much less than omega epsilon, that is, if sigma is less, means tan theta is very small. That means this material is a lossless or perfect dielectric. But if sigma is very much greater than omega epsilon, then tan theta is very large. So that comes under the category of a good conductor. Now we'll see what is the relation between the loss angle, which is theta, and the angle of intrinsic impedance, which is theta eta. So we know that eta is root of j omega mu by sigma plus j omega epsilon. So if you take a mu from the numerator and epsilon from a denominator, this expression reduces to root of mu by epsilon, root of 1 plus sigma by j omega epsilon. That is, we are dividing numerator and denominator by j omega. Now, this can be written as root of mu by epsilon into 1 plus sigma by j omega epsilon raised to minus half. And it forms a Taylor series expansion. And on expanding this, before expanding, we are taking the square. So, eta square is mu by epsilon into 1 minus sigma by j omega epsilon whole raised to minus 1. So when you expand it, it is mu by epsilon into 1 minus sigma by j omega epsilon plus etc. That is, we are ignoring the higher order terms. So the angle corresponding to eta square can be taken from by considering just the first two terms. We are neglecting the higher order terms. So the angle turns out to be tan inverse omega by epsilon. So when you consider eta, it is having a magnitude and an angle. So it is magnitude eta e raised to j theta eta. So this, when you take the square, it is eta square equal to magnitude of eta square e raised to j to theta eta. So when you take the angle of eta square, it is 2 theta eta. And this is equal to the value tan inverse sigma by omega epsilon. So we can conclude that tan 2 theta eta is equal to sigma by omega epsilon, that is already equal to tan theta, which is the loss tangent. Hence, we can conclude that theta is equal to 2 theta eta, where theta is the loss tangent and theta eta is the angle of intrinsic impedance. And now when you observe the range of values which theta can take, theta varies between 0 and 90. Since it is tan theta, it means tan 90 will reach to infinity. So tan theta will be varying from 0 to 90. Since the maximum value it will take when sigma is very high, that means it is maximum of infinity. That means the maximum value theta can take is 90. Now when you consider the angle of variation of theta eta, it will be between 0 and 45 degree. So this gives us the relation between theta and theta eta. Now we have already seen the phase constant in beta in radians per meter. So in other words, this beta can be defined as phase shift per unit length, that is beta equal to 2 pi by lambda. Now using this, we can find the velocity of the electromagnetic wave, which is u. So when you consider u, general expression for velocity is u equal to f lambda. Now when you multiply and divide this equation by 2 pi, this reduces to 2 pi f divided by 2 pi by lambda. What is 2 pi by lambda? It is beta. What is 2 pi f? It is omega. So velocity u can be written in terms of omega by beta. So this is the relation between velocity, frequency and phase constant. So we will conclude this lecture on electromagnetic wave propagation, where we have discussed the wave equations corresponding to EM waves, its solution, and terms like loss tangent, attenuation constant, phase constant, etc. Thank you.